So here we are with the Chapter 2, Section 3, Day 1 notes. We're going to describe end behavior of a polynomial function, and we're also going to review a little bit of factoring. Alright. So the first theorem here that we have is Theorem A, and the idea is that any polynomial of whatever the highest degree is, degree n in this case, can have a maximum of n solutions. So remember that solutions is a lot of different things, but it's x-intercepts. It also could be roots, and then it also is known as zeros. So anyway, it turns out that, for instance, if you have as we see here, a cubic function, right, so a polynomial of degree 3 in this case, has a maximum of 3 solutions. So taking a look at this first one, we have only one intersection, so that's only one solution. But this next one is also a cubic, and it has 1, 2, 3 x-intercepts or solutions. So that's just that theorem for this cubic function. The next theorem says that a polynomial of degree n can have a maximum of n minus 1 maximums and minimums. And when we're talking about maximums and minimums, we're talking about those local ones. Okay, so taking a look even at this cubic function, so again, this polynomial has a degree of 3, right, these two down here, and they can have a maximum of 3 minus 1 maximums and minimums. So here we are with 1 maximum and 1 minimum, so that's 2. And then 1 minimum and 1 maximum, again that's 2. And that's the most that can happen, okay? Depending on what's happening, you could actually just have a cubic that doesn't even have a local maximum or a minimum, just has what we will later call an inflection point. So that can happen, but again, at most 2 maximums and minimums. And then if we take a look at Theorem A and B for this second piece, for this quartic or fourth degree polynomial, you'll notice that looking at our first one, a degree of 4 can have a maximum of 4 solutions. So this one happens to have 2. This one also has 2. But depending on how it's drawn, what if it actually went down and then back up here? Then you could have 4. Okay, and that's perfectly acceptable because, again, the degree was 4. For the second theorem, Theorem B, if n is 4 in this case, we can have at most 4 minus 1 maximums and minimums. So taking a look, both of them actually have that maximum because we have 1, 2, 3 local max and mins, and then again 1, 2, 3 local maximums and minimums. So those are just what we're seeing here, and that will help us when it comes to talking about the end behavior because we need to know what happens in the middle to get to those ends. So the next thing we're going to talk about is end behavior, okay, and we use end behavior with this notation here that we have seen in Algebra 2, so hopefully this isn't too new, but either way, we use a limit notation to describe what happens on the horizontal ends of the graph. So notice that's in parentheses because, for instance, a polynomial doesn't necessarily end, right? It's going on forever, but doesn't go up or down is kind of the end that we're looking for. So, taking a look at this one here, this is saying the limit of the function. So again, this word here is limit, and this is function, whatever it happens to be. And then it's as x approaches, that's what that arrow means, negative infinity. So we're just going to say the left. And even I'll change approaches to goes to, because we may as well get really basic. There we go. So, again, this one here is saying the limit of the function as x goes to the left, and it's either going to be down or up. Okay. The next one is the same, only now instead of to the left, it's going to be to the right. So as x's go to the right, again, it's either going to go down to negative infinity or up to positive infinity. So these are the pieces that you would actually put after the equals sign, one of those two, just to say that it goes up or down. So here we are with one of our images, and even though it doesn't have them, there are arrows here, so we know it does continue. Fun story, there was actually a student my first year working here who thought that the limit was this. Like the last number was that one just because the grid was there. Totally makes sense, but again, because the graph itself doesn't have the arrows doesn't mean that they're not actually there. Okay, so anyway. Here we are. This one again is saying what happens as it goes to the left. And then this one's asking what happens as it goes to the right. So here we are with the left, and so where is it going? Negative infinity. And here we are with the right, as it's going to the right. And again, it looks like we're saying up, but the idea is that the right is going to continue right. Okay, and so it is right and up, and of course the up is then taken into account with the positive infinity. And the right is taken into account with the x's going that way. All right. So just a little review. Remember that if you happen to have a function, usually in this case we're probably talking about the function of x squared, but any function, even a cubic function or a fourth degree polynomial, all of them have this same idea. If there is an a out front, you are vertically stretching whatever it happens to be. If it's negative, whatever it is flipping across the x-axis, which will change what you imagine with your end behavior, which is what we want to note. B is your horizontal stretch or compression, and again, usually we won't end up doing this one because you can end up making it into the A, so we don't really need to talk about B. H is going to be your horizontal movement, so if anything is happening, adding or subtracting to that H, you're moving horizontally, and then your vertical movement is anything that's added or subtracted after the function has been altered. So, as we move through this, our next piece is factoring. So what we've talked about already is going to be in that book lesson, and then there's going to be a worksheet on factoring. So, if we remember back to factoring a polynomial, the first place to start is a greatest common factor. So sometimes, as unfinished as it feels, you are going to actually just have a number that divides out, or even a number and a letter, so just an expression that divides out of the pieces of the polynomial. So for instance, if we take a look at 2x squared and 4, the greatest thing that can divide into them evenly is 2. And so 2 goes out front of the leftovers. So 2 over 2 reduces to 1, or x squared, and negative 4 over 2 reduces to 2. So this is the factored polynomial, and all we did was take out the 2. I did, of course, double check if this next piece was a difference of squares, which of course is what this is trying to say here. But it's not, because 2 itself, 4 was, but 2 itself is not a perfect square. So, alright, so the next piece we're looking at the numbers 16 and 81, and neither of them have a number alike that you can divide into them, but I am seeing, especially since it's down here, that this is a difference of 2 things squared. So first of all, if I take the time to rewrite this as something squared, there's a 16, which is actually 4 squared, and an x squared, which is actually an x alone that could be squared. To that, in another square, I can also put 9. So what I've just figured out is that in this formula, if you use that, my a value would be 4x and my b value would be 9. So writing it out the way they have it, or if you remember from our previous years, you're just going to take those two pieces of 4x and 9, repeat them, and put a positive between the two pieces and a negative between the two pieces. So this is the factored out piece. Again, why would you need a factor? Remember that that's going to allow you to find the zeros a lot quicker, or any vertex, that kind of thing. So factoring is very helpful when you're trying to solve a polynomial. Then the next one, notice that we have a 4-term polynomial. And so because we have a 4-term, we're going to factor by grouping, which means that we are going to group these two pieces, find the GCF of each of those two pieces, and then we'll realize that what we have left over is also the same. So we're going to basically do 3 greatest common factor problems. So looking at this first set of factors, of terms, we have a 6 and an 8, so definitely a 2 can come out of both of them. And then the lowest power is b squared, so we can also take that out. So we'll have 2b squared that's taken, or divided in fact, out front. And then the results of 6 divided by 2 is 3. B cubed over b squared leaves a b. And then 8 over 2 leaves a 4, and b squared over b squared will be 1. In the next piece, we have a 9 and a 12, so a 3 comes out of both of those. But only the 9 has a letter, so we're not going to take out a letter from both of them. So just a 3 takes out front. 9b divided by 3 leaves 3 and a b. And 12 divided by 3 leaves a 4. Hopefully we see that both of these are the same. And so officially we're going to take those sets out front. So we'll have 3b plus 4. And then the leftover of 2b squared plus 3. Again, there are those of you who are going to say, but where did the other 3b plus 4 go? Well, in that case, then why aren't you asking me where did the other 3 go, right? Or where did the other 2b squared go? So the idea is that it didn't go anywhere. We just made it simpler by taking it out front. I could redistribute, which would make it back to being twice in there, right? Distribute to 2 things means it was twice there. And that's what would happen here. I'd redistribute this to the 2b squared and this entire thing to the 3. So it's still there, we're just simplifying it so that we can group it. Alright, so the next example is just going to be your basic factoring of a 3-term polynomial, where all you're doing is trying to find what multiplies to the c value, and at the same time adds to the b value. So if you were in the class last year, these are those x things where you put c here, the value, and b, and then you're trying to find these 2 pieces over here. So taking a look at this first one, again, I'm trying to find out what multiplies to be negative 20, and at the same time adds to be 1 in this case, the middle leading coefficient. So, first thing that I'd want to do is, if you don't know, list out the multiples of negative 20. So we've got 1 and negative 20, and negative 1 and 20. 2 and negative 10, and negative 2 and positive 10. 4 and negative 5, and negative 4 and positive 5, and that's it. So all we have to do is find out which one adds to be the positive one, so that's these. And so that means negative 4 and 5 are our terms that we'll put in with our factor parentheses. So x squared plus x minus 20 actually equals x minus 4, and then x positive 5. So that's the factored version of it. Same thing would happen to this next one. So we're trying to find what multiplies to be negative 18. And adds to be negative 3. And so if we list out the factors of negative 18, and again, if you don't need to list these out by actually writing them, that's perfectly acceptable, but just so that we know where we're all getting this from. And you're wondering how I'm getting each of these, and I'm literally just going through the numbers. Does 1 work? Does 2? Does 3? And I just go through it until I get to the middle of the number. So 2 and then 3 and negative 6, but then also negative 3 and 6, 4, no, 5, no, 6 already did. Alright. So which ones add to be, in this case, negative 3? That's these. So we're going to have 3 and negative 6 as our pieces in the factors. So again, we've got x and another x, but this time we're going to get plus 3 and minus 6. Remember, it doesn't matter which one you put first, so if you want to go ahead and put minus 6 and then plus 3, perfect, because it's multiplying, so it's okay if one term comes before the other. It would not be okay if you wrote 6 minus x. That's where there's a problem. Alright. So, taking a look at our next piece, this is where we're factoring with an a that is not 1. Okay, so the problem is that in our previous examples, notice that we didn't even look at the fact that it was an x squared. Okay, maybe you did, maybe you didn't. But now if we look at our next examples, we're going to have to use this kind of master box, okay, because of the fact that there's something other than 1 out front. So we'll have to take out some sort of GCF. So there are 2 ways of doing this. You can either use the box or you can use the grouping method that we used last year. And so I'm going to go ahead and do one of them with the box and then one of them with the grouping method, unless I forget, and then I'll probably just do both of them with the box. Okay. So if we fill in the box, the first thing that we do is fill in diagonally what we have. The next thing is trying to figure out what multiplies in this case to 2 times 21, which is 42. So we want it to be multiplying to be 42, but at the same time adds to 17. So again, it's not 21 anymore. Now there's a 2 in front, so we're actually going to list all the factors of 42 that might add to be 17. So 42 can be 1 and 42, but you can also do negative 1 and negative 42, which I can see since I'm trying to get positive 17. I don't really need this list. We also have 2 and 21, and let's see, 3 and something, 14. And of course, since I just found it, I don't necessarily need to continue. So in that case, I'm going to put 3 and 14 in here, but they do need an x next to them. Otherwise, when you go to take the GCFs of certain columns and rows, you won't have anything that's alike. So 14x goes here, 3x here, or switched. Okay, but the idea is that now we're going to take the GCF of every column and every row. So for instance, this top row, we have a 2 and a 14, so at least a 2 can be alike in there. And then we have an x squared and an x, so at least an x. The next row we have 3x and 21, so at least a 3 can come out of both of them. But then not an x, right, because there isn't an x here. Then if we look at this first column, a 2 and a 3, they're both prime, so there's nothing alike there. But the x squared and the x, we can at least have an x that's alike. The last column has 14 and 21 as our numbers, so a 7 is alike in both of those, but of course not an x because they don't have those. So if you take a look at this, our factors are actually x plus 7 from the top and 2x plus 3 from the bottom. And so that's how we get without a leading coefficient of 1, so in this case 2, we can get our factors that way. Alright, so the next one I was going to use grouping. So same process to begin with, though. We need to find what 3 times 16 is. So 3 times 16 is 48. So we need it to be multiplies to 48 from 3 times 16. And then if we list all of our factors of 48, remember that we need something that adds to be negative 16 in this case. So again, there's negatives, so I do want to include my negatives and my positives in this list. So 1 and 48, but then also negative 1 and negative 48 are an option, or a pair. I also have 2 and 24, or negative 2 and negative 24. Again, keep in the back of your mind that we're trying to get negative 16, so you can stop when you get there. Alright, positive 3 works in there. Yep, 0 and 16, because we just did it. And so negative 3 and negative 16. There's also 4 and 12. And negative 4 and negative 12. And I'm going to stop there, because guess what? Those add to be negative 16. So now we're actually going to do factoring by grouping, by rewriting this as 3x squared, yes, and plus 16, yes, but minus 4x and minus 12x in the middle. So I've rewritten this original negative 16x as negative 4 and negative 12x's. Then I go through and factor by grouping. So if I divide out an alike factor in both of these, it's just x. So x out front, and our leftovers of 3x minus 4. And then what comes out of the second piece is a negative 4. If you just tried a 4, you would not get the same second piece here, so negative 4 ends up being what we're taking out. So negative 4 leaves you with a positive 3x, as our previous grouping has, and then a minus 4. Again, those two pieces in black are alike, so we're going to take those out front. And then the leftovers are an x and a negative 4. And so again, that's the grouping way, and then the previous problem is the box way. So you do have an assignment, and again, there's a book piece, which is going to be about that end behavior, and then there's also a factoring worksheet.